In the last lesson 5, we have seen how to describe the fugacity coefficient for a volatile in the gas phase, either pure or as a component in a mixture, such as a mixture of water and carbon dioxide. To do that, we need an equation of state for the real behavior of the gas phase, covering from zero pressure, where the gas phase behaves ideally, to the pressure of interest. With such an equation of state, we can obtain the fugacity coefficient in terms of the integral of the difference between real and ideal molar volume for a pure component gas phase, or between real partial molar volume and ideal molar volume for a component in a gas mixture. In other words, given an equation of state for the real gas under investigation, that is, an equation which gives us the volume of the gas as a function of pressure, temperature, and composition, the problem is fully solved. Now we move on to the next quantity that we need in order to complete our model of multi-component gas-liquid equilibrium in magmas, namely the reference fugacity of each volatile component in the liquid phase. We will see that once again, what we need is an equation of state, this time for some reference state that we need to define, appropriate for the volatile dissolved in the liquid phase. Let's start by recalling the expression for the fugacity of a component in the liquid phase that we derived in lesson number 3. First of all, a very important point that I'm repeatedly stressing throughout these lessons. The reference state must refer to the same temperature as that of the system for which we want to make calculations. If you don't remember why, you can have a look back at lesson number 2. Second very relevant point, the activity coefficient gamma and the reference fugacity F0, which appear in this expression, are not independent. They concur to the definition of fugacity, which is determined from a reference state F0, which I just said it is defined at system temperature, plus a deviation from that reference state described by the activity coefficient gamma, which accounts for the specific conditions of pressure and composition, in general different from those of the reference states. We will explore the activity coefficient in the next lessons. What is important here, again, is to understand the link between reference fugacity and activity coefficient. When defining a reference state, we are also defining the activity coefficient, as the activity coefficient describes the deviation from that selected reference state to the effective state of the component in the mixture. In other words, the job of defining the fugacity of a component in a liquid mixture is partitioned between the reference fugacity and the activity coefficient. In principle, any choice of the reference state is possible. The reference state is not univocally determined. Making a good choice is up to us. Some choices are better than others, as they result in a clear partition of the job between the activity coefficient and the reference fugacity, and they simplify the calculations. In other words, defining a reference state is a matter of convenience. While a smart choice makes the problem manageable, a wrong choice may make it a nightmare, or it may even make it impossible to solve. Making a smart choice for the reference state is therefore part of what we refer to as the art of modeling. Here is a choice that in many situations characterized by ample compositional variability turns out to be a smart one. Let's assume there is some hypothetical state associated to each dissolved volatile, and that describes the behavior of the pure dissolved volatile. Well, this short statement here requires some explanation. First of all, referring to a hypothetical instead of a real state is not at all a problem in thermodynamics. On the contrary, that's quite common. We have already seen ideal conditions, which is also a hypothetical state, to which real gases stand when the pressure approaches zero. That means exactly that there is no ideal conditions in the world, although there can be conditions and problems for which an ideal approximation can be taken. Ideal conditions are often employed as a reference for thermodynamic calculations, although that reference, strictly speaking, does not exist in nature. It's only hypothetical. That's one of the big advantages of thermodynamics, that it does not necessarily need to refer to conditions that exist in nature. We can equally refer to some idealized or hypothetical condition if we can describe the thermodynamic properties of such condition and those along the whole path from it to the effective conditions of interest. That is not different from what we have seen in the previous lesson, where the fugacity coefficient for a gas phase is computed based on the whole path from ideal to real state, or from zero pressure to system pressure. The same concepts can be applied to the liquid state and to the reference fugacity in the liquid state. Second element included in the highlighted statement, and that requires some explanation. I refer to a hypothetical state represented by the pure dissolved volatile component, not the pure component, such as pure water or pure carbon dioxide, as that would be too far from the liquid magma. And for us, describing through the activity coefficient the deviation from the pure component of the component to the component dissolved in a real multi-component magma would be too difficult, maybe nearly impossible, and in any case not a smart choice. We are instead referring here to a hypothetical state, something which does not exist in the real world. Not a problem, as we just said. A state where the dissolved volatile is a pure liquid with a behavior similar in some way to that of the volatile component dissolved in the liquid mixture. For the moment, let's assume we have an equational state for such a weird state. That is, an equational state for water dissolved in the liquid magma as it was a pure component. And similarly, an equational state for carbon dioxide dissolved in the liquid magma as it was a pure component. If we have an equational state for such a hypothetical state, we can then use it as a reference. The second part of our smart choice is that of taking the reference not only at system pressure, as it must be, and as I repeatedly, continuously during these lessons, but also at the same pressure as that we are interested in, giving therefore the activity coefficient the exclusive duty of describing the deviation of the fugacity as due to the real liquid composition with respect to the hypothetical pure dissolved volatile component. That is what the equation here says. that the reference fugacity is chosen to depend only on pressure and temperature, while any compositional role in defining the fugacity of the dissolved volatile is entirely ascribed to the activity coefficient. Okay, we have a choice for the reference state, but how do we implement it in practice? We know that we need an equation of state for the theoretical, hypothetical, pure dissolved volatile that we still don't have. But even if we had it, how would that define the reference fugacity? That's what we are up to see. Well, we said that we select the reference fugacity for a volatile dissolved in the liquid phase to be only a function of pressure and temperature, because the effects of the liquid magma composition will be ascribed entirely to the activity coefficient. We can then introduce the logarithm and differentiate. This is just a mathematical operation and there is nothing to understand here. The next step is to express these two terms here, which describe how the logarithm of the reference fugacity changes when either pressure is changed at constant temperature or temperature is changed at constant pressure. We can find exact expression for that by just employing relationships that we know very well, namely the expression for the chemical potential in terms of fugacity and the differential expression of the chemical potential, recalling again that the chemical potential corresponds to the molar Gibbs energy. If you need to refresh your minds, have a look back to lesson number 2. Here is a new exercise. You can either try to solve it or skip it and continue with the presentation. As usual, in both cases, you will see the solution in the following. The exercise is this one. Employ the two expressions above for the chemical potential and its differential to express the two partial derivatives on top in terms of only volume. Note that this exercise requires a bit more analytical efforts than other exercises in previous lessons. But if you did them, and if you take enough time to do this one, you will succeed. As usual, I have a suggestion for you. When dealing with the temperature partial derivative, remind the relationship between Gibbs energy and enthalpy that I showed in lesson number 1. Press pause now if you are doing the exercise. Okay, here we go. Let's consider the two pressure and temperature terms separately. And let's start with the pressure term. Here, I am writing again the two basic relationships for chemical potential and for its differential that I anticipated we need in order to proceed. Once again, we refer to a hypothetical state of pure component dissolved in the liquid. For a pure component, we can employ the expression for the chemical potential to obtain an expression for the logarithm of fugacity. On this expression, we can then apply the pressure partial derivative operator. μ0 and f0 correspond to some reference states that, as we know well from lessons 2 and 3, must have the same temperature as that of the system. Therefore, it depends on temperature. Whereas it is commonly defined at some reference pressure, such as 0 pressure or 1 bar or some other given value. μ0 and f0 can therefore be defined to not be a function of pressure, and the corresponding terms disappear when deriving pressure. Now, let's have a look at the expression that we have obtained. The right-hand side term contains the pressure partial derivative of the chemical potential. We can then employ the second one of our expression on the left, which tells us that the pressure partial derivative of the chemical potential is equal to the molar volume. By substituting, we obtain what we were looking for, that is, an expression for the pressure partial derivative of the logarithm of fugacity of a pure component in terms of its molar volume. Because our reference state is that of a pure component, although a hypothetical one, this expression is directly applicable to replace the first term in the fugacity differential on top. So we know how the fugacity varies with pressure, and that depends on molar volume. Let's only note that we still do not know how to express the molar volume of the hypothetical dissolved volatile. This is something that we leave for a next step. For the moment, we only want to express the differential of fugacity for our hypothetical reference state of pure volatile dissolved in the liquid phase as a function of volume only. We'll see later how to represent volume itself. So the pressure partial derivative of the logarithm of fugacity is done. We now need to deal with the temperature partial derivative, that is, the second term on the right-hand side in the equation on top of this slide. Let's do it. And again, we employ the expressions for chemical potential and for its differential that we have already used for the pressure partial derivative. Now, the procedure is slightly different because, contrary to the case for pressure, the reference state is a function of temperature. I have stressed this repeatedly throughout these lessons, but if you want to refresh your memory on why the standard states must depend on temperature, just go back to lesson number 2. Because the reference state depends on temperature, when evaluating the temperature partial differential of the fugacity, the reference terms do not disappear, as it was the case for the pressure partial derivative. With this in mind, let's proceed. First, we obtain the logarithm of fugacity from the expression of the chemical potential and select the reference state so as to correspond to a condition where the system behaves as ideal. The superscript plus here refers to ideal conditions. Thus, the fugacity F0 corresponds to ideal conditions where fugacity and pressure corresponds, and it is substituted with P plus, that is, the reference pressure where the system behaves ideally. Similarly, mu0, the chemical potential at reference conditions, can be written as mu plus, that is, the chemical potential at ideal conditions. The second one of our starting expression on the left tells us that the temperature partial derivative of the chemical potential is equal to minus molar entropy. By differentiating the first expression in temperature at constant pressure, we then obtain this expression for the temperature differential of the logarithm of fugacity. You can stop here and do it yourself if you want to check it. Now, just cancel one R in all terms on the right and recast the denominator terms in this way by taking together the terms that refer to system conditions and to reference conditions, the terms with the plus, recalling that we have chosen to refer to ideal conditions, therefore the plus terms refer to ideal condition. This is the same expression reported in this new slide. Now, what do we have at the denominator? We have the difference between a quantity placed within brackets at system and at reference or ideal conditions. Once again, note that the temperature of the ideal reference is equal to system temperature, and it couldn't be different. We are continuing to repeat this again and again. What does the quantity in the brackets represent? Let's go back to the expression of the Gibbs energy to understand that. We obtained this expression in lesson 1 from just the first and second laws via Legendre transformations. Gibbs energy is given by enthalpy minus the product of temperature and entropy. If we write it for a mole of substance and remind that the chemical potential is the molar Gibbs energy, we see that the quantity which appears within the brackets in our expression is exactly molar enthalpy. Thus, we can substitute and obtain a compact expression for the temperature partial differential of the logarithm of fugacity. This is the expression that we were looking for. So, we have started from a general expression for the pressure-temperature differential of fugacity, or more correctly, its logarithm, and have come up with a nice compact expression telling us that the change in fugacity, when slight changes in pressure and temperature occur, depends on molar volume and molar enthalpy. This is a fully general expression. In our case, we developed it in order to describe a reference state for the volatile dissolved in the liquid phase that we selected to correspond to a hypothetical pure dissolved volatile. Thus, the molar volume and the molar enthalpy in this expression refer to such a hypothetical state. Again, keep in mind that we don't have yet any equation of state for the hypothetical state. That's something that we are delaying to a later stage. For the moment, we assume that we will be able to find a proper equation of state. Assuming that, we can simply integrate the differential equation to obtain an expression for the reference fugacity in the liquid phase. Here, the first term at the right-hand side represents fugacity at some reference pressure and temperature, identified by the 0 at the superscript. Do not get fooled by all these references. True, we are searching for the fugacity of a reference state, that is the quantity on the left-hand side of this equation at the bottom, and we express it in terms of the fugacity at one other reference state. But that's how thermodynamics works. Thermodynamics deals with changes from one state to another. Therefore, quantities such as the Gibbs energy or its smaller counterpart, the chemical potential, as well as many others, are only defined in terms of differences from one state to another. Here we want to express the chemical potential, or equivalently, the fugacity, for a volatile dissolved in the liquids. We said it's convenient to refer to a hypothetical state and compute the changes from that hypothetical state. But the fugacity for the hypothetical state also depends on pressure and temperature. Therefore, there is nothing strange in computing it in terms of deviations from the fugacity value at one other state where pressure and temperature are fixed. At fixed given pressure and temperature, and for a given pure volatile, no matter if real or hypothetical, the fugacity is no more a variable. It is just a number. Thus, if we are able to find an equation of state to use within this equation at the bottom, The same equation will tell us how the fugacity of the reference state varies as a function of pressure and temperature from some constant value defined at some fixed pressure and temperature. It may seem a bit tricky if you are not much used to thermodynamic modeling, but that's how it works. Okay, that's all great, but we have not yet finished. In fact, we can still develop this equation further. As it is now, it requires that for our peculiar hypothetical reference state of pure dissolved volatile, we know both volume and enthalpy. We can simplify it further and get to an expression where only the volume of the hypothetical state is required. That is, in fact, the essence of any thermodynamic computation. Given a relationship between pressure, temperature, and volume, an equation of state, we can express any other thermodynamic quantity. Let's see it more, or in other words, let's see how enthalpy can be replaced by volume. Here is the integral term from the previous equation containing molar enthalpy that we want to rewrite in terms of molar volume. As usual, we start from fundamental relationships that we know from lessons 1 to 3. In fact, all of the necessary theoretical basis for our developments was defined in lessons 1 to 3, making up the theoretical unit 1 of this training module. From the first and second laws of thermodynamics, and after application of the Legendre transformation, we know the differential expression for enthalpy and Gibbs energy, here written for 1 mole of substance, recalling again that the molar Gibbs energy corresponds to the chemical potential. From the first expression, we obtain the pressure partial differential of molar enthalpy, that we find to be a function of the pressure partial differential of entropy. From the second expression, we obtain the pressure and temperature partial differentials of the chemical potential that we have used already in the previous slides. Here, a mathematical relationship known as the Schwarz identity comes to help us. The Schwarz identity allows us to exchange the variables in a double partial differentiation. In a nutshell, it says that for a function z differentiated in x and y, the order of variables in the partial differentiation does not count. We can differentiate z in y at constant x, take the result and differentiate it in x at constant y, or do all the reverse, and the result is the same. Let's apply it to molar entropy, which appears in the equation at the top right, by making use of the expression for the partial pressure and temperature derivatives of chemical potential. We can write the pressure partial derivatives of entropy by substituting this expression for entropy. Now we have a double partial differentiation. Therefore, we can apply the Schwarz identity and replace the order of differentiation. That is, replace pressure with temperature and vice versa. The internal differential is equal to molar volume. Therefore, we finally find that the pressure partial differential of entropy is equal to minus the temperature differential of volume. By substituting, we can finally rewrite the pressure differential of enthalpy in terms of volume only. Here is the same expression. And again, the integral term where we want to replace enthalpy with volume. In the integral term, we have the difference between molar enthalpy at real and ideal conditions. If we consider the pressure differential of that difference, we see that it is equal to the pressure differential of the real part only, because the ideal part only depends on temperature. We know it must depend on temperature, and as usual, we refer it to a given pressure, that is, a constant pressure, where the system behaves as ideal. We can therefore obtain an expression for the enthalpy difference by integrating from ideal to system conditions. You may want to press pause here to check better the operations that have been done. Here is the same expression, and again, the integral term where we want to replace enthalpy with volume. At this point, all the elements are there. Just replace the expression on top, and we find that the temperature integral term containing enthalpy can be replaced by a double integral containing only volume. This is the expression for the reference fugacity we have started from. Now replace the enthalpy term with the double integral, and in doing so, just select P0 as a pressure at which the volatile behaves ideally. That is, a pressure at which P plus and P0 coincide, and finally obtain an expression for the reference fugacity of a hypothetical pure dissolved volatile as a function of its molar volume only. That is what we were looking for. Let's look at it more carefully. As we discussed already, this term is just a constant. In other words, it is a number, one for dissolved water and a different one for dissolved carbon dioxide. We don't know the value of this quantity, but we can treat it as a parameter in our final system of equations and constrain its best value by comparison with experimental data. Remember here an element introduced during lesson 4. We may, in principle, obtain a complete model of volatile magma interaction thermodynamics by just first principles, relying only on electron orbitals and fundamental interactions. Similar models are being produced, but they are hardly applicable to real complex problems, as the computational power they need is exceedingly large. In our approach, based on classical thermodynamics, we do not employ the fundamental forces governing the interactions between atoms and molecules. That necessarily requires constraining some quantities from the experimental data. We'll see that in much more details in the next lessons. Second relevant aspect of this expression, the reference fugacity is defined from knowledge of only the volume of each hypothetical pure dissolved volatile. We need an equational state for each hypothetical pure dissolved volatile, covering any pressure and temperature condition from those of interest down to the lower boundaries of the integration where the hypothetical pure dissolved volatile behave ideally. We have not yet defined such equational state. We will deal with that at a later stage, after having explored the activity coefficient and its relationships with the Gibbs energy of the mixture. Okay, we are at the end of this quite technical lesson. A short summary, as usual. As the reference state for dissolved volatiles, we said we can use a hypothetical state represented by the pure volatile component dissolved in the melt. That's totally hypothetical, but this is not a problem in classical thermodynamics. In fact, that turns out to be a smart choice, and we'll see it further in the next lessons. All of this lesson was then dedicated to derive an expression for the reference fugacity of such a hypothetical pure volatile component dissolved in the liquid, as a function of only its molar volume. To use that expression, we still need to define an equation of state for such a hypothetical pure volatile dissolved in the liquid. But we have left that suspended for the moment, and we'll go back to it after having dealt with activity coefficients. After all, we have said repeatedly that reference fugacity and activity coefficients team up to define fugacity. Therefore, they are intimately related. It is therefore inevitable that the choices we make for one also impact on the other. With the next lesson, we will talk of that, and we will enter the world of real mixture more deeply, exploring what happens when we take separate components and mix them together. And from that, we will discover what the activity coefficient really is, much beyond its definition that we gave in lesson 3, where we introduced activity coefficients as simply the ratio between activity and mole fraction. That will be the content of the next lesson 7. I'm waiting for you there.